So it's x cubed minus x squared minus x plus 1. But then we have to come through here and change the signs again. So this becomes minus, plus, plus, and then that becomes a minus. Obviously, I like to exaggerate those so that I don't mess them up. What do you have here? Just 4x, and that's it, right? Everything else goes away. So x cubed goes into x, how many, you know what I'm saying. What do you multiply x cubed by to get 4x? You can't, right? So that's your remainder over your divisor. All right. So now, that means that this integral up here is actually a new integral. It's the integral of x plus 1 plus 4x over x cubed minus x squared minus x plus 1, all of that dx, right? Now when we look at this, instead of this, right, this is what it started as, but we did the division, turn it into this. Now the first two terms we can integrate without much effort, right? 1/2 x squared, x, we're done. The only question is how do we do this, right? So for this right here, we have to go do the partial fractions on it, right? So our first step was long division. Now we move on to partial fractions. And we're only going to be doing partial fractions on one of those terms, right? That's only one of them that we have to worry about. So now this is, on the side I'm doing this scratch work. I put 4 over x, or 4x over x cubed minus x squared minus x plus 1. And now I get to go and do my little partial fraction thingy. So what's the first step of this part? Factor, denominator. Well, it's not a quadratic or it's not a trinomial, right? So we can't use that. But how many terms are in my denominator? 4. So what's the standard thing you do when you see 4 terms? Grouping. Factor by grouping. Now grouping doesn't always work, but it's what you want to try when you see 4 terms. So I'm about to factor by grouping in the denominator. So I look at my first 2 terms. I like to draw a little slash right past the second term, like that. And then what you do is you do like a GCF, a greatest common factor, on just these 2. So you're like looking at these individually now. So what's a factor I can pull out of both of these? X squared. So if I pull an x squared out of the first 2, I'll have x squared, and then what would be there if I pulled an x squared out? X minus 1, right? Now on the second 2 terms, I want to be able to factor something out that would make it match this x minus 1. So I have to pull a negative 1 out. If I pull a negative 1 out of these 2, it'll leave me with an x minus 1. The whole goal of factoring by grouping is to have these 2 match. Those 2 have to match, right? And they do, all right, in this case. So I had a conversation with my other class about this. I did something on the next step, and they're like, some students after class are like, what did you do there? So just to be, I'm factoring out the factor. Yeah, so let me do it this way. This might help. If I gave you this expression, x squared m minus m, could you factor out a GCF, greatest common factor? Right? What do they both have in common? An m, right? So I pull an m out, and then you'd write x squared minus 1, right? Okay? All right, so that's exactly what I'm doing here. I have x squared times m minus m, right? So I'm going to pull the m out, but m is actually x minus 1, right? I'm going to pull the x minus 1 out. And then what am I left with when I pull the x minus 1 out? X squared minus 1. Now I'm bringing this up because it's a lot of times when students are taught to go from this line to this line, they're just told, okay, just write x minus 1 down and then just write x squared minus 1 in parentheses. And they're not really told like why, but that's the algebra of what's happening. You're actually pulling out the x minus 1, and it leaves you with this. Okay? All right, are we completely factored out now? No. We have a difference of squares there, don't we? That's a difference of squares. So now we're at 4x over, we had an x minus 1 out there, and then difference of squares is x plus 1 times x minus 1, right? Are we completely factored out now? Yes. All right, now we need to do the part where we recognize what type of factors we have. They're all linear, right? But they're not distinct because these two factors are the same, aren't they? So I'm going to rewrite this like this. That's the same thing, right? You have two x minus 1 factors. So multiplication, I can just slide them together. That's this. So now what we have, these are both linear, aren't they? That's a linear factor. This one is a linear factor, but it's repeated. So how do we deal with that? Well, partial fractions, this is the way we do it. For each linear factor, we have to put like a over the linear factor. Okay, so that's kind of like from the previous problem. But if we have a repeated linear factor, what we do is this. And this is kind of weird. We do b over the linear factor plus c over the linear factor squared. And that's just the procedure. That's just the way it's done. So do you see that it was power 2? So I started out b over x minus 1 to the first power, then c over x minus 1 squared. Had this been the fourth power, not second, then what would I have done? I would have had this, then plus d over that thing cubed plus e over that thing to the fourth. And then I would have stopped. So that's how you deal with repeated linear factors.
Is there a case where it's like a plus b plus c?
Next example. Okay. Yep. All right, so that's it. Any questions on that? What we need to do now is try and get a, b, and c. So we need to clear fractions out again. So let's multiply both sides by the denominator on the left side. So I'm multiplying everything by this, right? So on the left side we get 4x. That's always going to happen. The left side's always going to be just your numerator. Now, I'm not going to write it down over here because I want you to try and do this mentally. Just think that each one of these is being multiplied by that, right? Each one of those. So what cancels is what you need to figure out. So what would cancel here? The x plus 1, so you'll have the a still. And then you'll have the x minus 1 squared. Plus, on this one, what would cancel? Just one of the x minus 1s. So you would have plus b, you still have the x plus 1, and you still have one of the x minus 1s, right? And then on this one, the x minus 1 squareds cancel, and you still have the x plus 1 and the c. All right, there it is. That's what we get to work with. Now, this is where we have to make a decision. Do we want to use the long method or the short method? Can we use the short method? So can you get A? Can you kill off B and C at the same time without killing off A? The x plus 1's common, right? So I could do that. If I let x be negative 1, do you agree I could kill this, and not kill this? Yes. Okay, so I could get A. Now, could you get B? To get B, I have to kill these two off. But they don't have any common factors. So I can't kill them off without killing off b, right? Could I get c? Well, yeah, I could let x be 1, right? So I could get a the short way, I could get c the short way, but I can't get b the short way. Now you could actually walk down that road. You could go figure out what a is, figure out what c is, then you could, there's a way you could get to it. But I mean, that was fun on the calculator, right? You bought it, right? Let's get some of the money worth, you know, get some of the value out of that. Right, you got this fancy calculator sitting there. You may as well use it for something, right? So let's go through this quickly. All right, this is, if I square that, that's x squared minus 2x plus 1. And then I have to hit everything with an a. So ax squared plus 2ax minus 2ax plus 1a, so just a. And then what about if I multiply these two together? That's x squared minus 1, isn't it? And then just distribute a b through. So bx squared minus b. And then the last one would be cx plus c. All right, 4x equals, let's get my x squareds together. So what are the coefficients for x squared? We have an a and a b, right? So can I just put a plus b and then x squared outside of it? That was these two right here. Now let's take a look at the x terms. I've got one there and one there, right? Notice how this one is negative 2a, right, in front of the x? Watch the way I write this. Plus parentheses negative 2a, then plus cx, plus c, and then x. See how I did that? Like I always put a plus here no matter what, and then whatever's in parentheses, if it has a negative, I put a negative, all right? Do you all agree with that statement there? And then what's my last term? Everything that doesn't have c. It's just plus a plus c. So it's kind of like both of these are together, right? Oh, minus b. Oh, crap. Oops. Ooh, almost made a mistake. Minus b plus c. See, this is why I think it's important to go in here and actually like circle stuff and underline stuff. You kind of make sure you don't skip anything. Like I've accounted for everything up there. Okay? All right. System of equations. Crap. This has to be the number that's in front of x. Ooh, there's no x squared. So it's a 0, right? So I know that a plus b has to be equal to 0. And I left a space here for the c's. This second equation right here, negative 2a plus c, is what's in front of x. So negative 2a plus c is what's in front of x. So that has to be 4, right? And then what about a minus b plus c? What does that have to be equal to? 0, because there is no number over here by itself without x. So you're kind of over here, you're visualizing that this is this. That's what the left side is. So the thing in front of x squared is 0. The thing by itself without x is 0. And then you got a 4 in front of there. All right. Into the calculator, we put 1, 1, 0, 0, negative 2, 0, 1, 4, 1, negative 1, 1, 0. Right? That's just reading off the coefficients here. And then reduced row echelon form. So I'm just waiting for somebody to give me an answer here.
Negative 1, 1, and 2.
Negative 1, 1, and 2? Okay. -1, 1, and 2 for A, B, and C. So now we go back to this, right? Remember this is where we were? And we just did partial fraction decomposition on this, didn't we? On just that part. So here's where we are in terms of the integral. We are at integral x plus 1 plus, what was it? A over what? X plus 1? So it's A, which is -1 over x plus 1, plus, and it was B over x minus 1, right? So B is 1 over x minus 1. And then plus C, which is 2 over x minus 1 squared. And that's it. So I know when I'm in pre-cal and I'm teaching this, partial fractions, I always tell them, look, partial fractions is a tool that we use in Cal 2. Well, it's used for other things, but specifically in Cal 2, we take a very ugly problem and we break it into a bunch of easy problems, right? That's what that technique allows you to do that. Otherwise, that would be a very difficult integral to do. Now let's do the antiderivative. All right, antiderivative of x, 1/2 x squared, right? Plus x. Minus natural log, absolute value, x plus 1. Next, plus natural log, x minus 1, plus 2. I'll pull the 2. Drum roll. U sub. Yep. This thing looks like 1 over u squared. Doesn't it? Kind of? Well, the 2's out. 1 over u squared, which is u to the -2. The antiderivative of u to the -2 is negative u to the -1. So this should be negative x minus 1 to the -1. Yeah, I'm going to put it over on the next one, all right? Do you all agree? The 2 came out, and then the antiderivative of that is this. And then plus c. So if I were to, I mean, I'm happy. I'm going to leave it like this. But you could maybe rewrite this as minus, like this last term, you could maybe write as minus 2 over x minus 1, like that. That's the same thing, right? All right, there it is. How are we doing on time? How are y'all feeling about this? It's a little tedious, right? Yes. Did I just erase something? What?
Yeah, I was going to ask you for the A, B, and C.
Yes.
Where you had B is 1 over
X minus 1.
And then C is
2 over
x minus 1 squared.
Mm-hmm.
Where did you get that?
In the very beginning, when we were doing, we said, how does this thing break down?
Right, but like, where did you get that from? Because like
That's partial fractions. That's what partial fractions is. So if you go back to these notes, let me go back to the notes, all right? Do you remember seeing partial fractions ever? Pre-cal?
Me?
No.
Oh,
Okay. So look, see, this is why I don't like reading the notes, because they look horrific. All right? If you take a rational function and you factor the denominator into a bunch of linear factors, so this is saying like, this is like x minus 3, maybe this is like x plus 1, and then, I don't know, you got a bunch of these, right? Then what you do is we will have to find constants, and I'm using A, B, C, and you put that over each linear factor, okay? That's what the first thing says for partial fraction decomposition. For every distinct linear factor, you're going to do a number over the linear factor. Now, why do they use subscripts? Why do we use subscripts in math instead of doing like A, B, C? You don't know why we use subscripts? To make it look worse than it is, yes. To make people not want to do math, exactly. No. What if you have a polynomial, a rational function where your denominator has 100 distinct linear factors? You're going to run out of letters, right? A, B, C, D, E, F, G. You're going to run out of letters, right? But if you subscript them, A sub 1, A sub 2, A sub 3, you'll never run out. That's why we do it. It's not for torture. It's because mathematically, we run out of letters. Okay. Now I use A, B, and C here because you're never going to get a system that's going to have 26 unknowns. Yes.
Is there a chapter in the book that goes over quadratic?
I do not believe so. I do not believe so. Okay, so part B says, what if you have a repeated linear factor? So this would be an example like, let's say we had, in the bottom here, let's say we had x minus 1 to the 5th power. Then what you do is a over x minus 1, b over x minus 1 what? Squared, c over x minus 1 cubed, d over blah, 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 until you get to the very end to the 5th power. That's what we just did. When we had x minus 1 squared, we did a number b over x. We didn't use a because we'd already used a for the other factor. So we did b over x minus 1 and then c over x minus 1 squared. That's what this is saying. Okay? And then, well, this is where we're headed, so we may as well do this. What if we have an irreducible quadratic factor? So what if we have a quadratic on the bottom that can't be factored? Then what do? We do a x plus b. So this is what you were saying. Do we ever see something like this? So we do something like this. Let's do the example. And then what if that irreducible quadratic factor is repeated? Then we have to do something over that, something over it squared, something over it blah, blah, until the power comes up to whatever it is. Same thing that we did with the linear, but we do it with the quadratic. Okay, look at this one right here. All right, do we need long division? No. Okay, so let's go straight to factoring. GCF, x, right? Pull out that common factor. Now, look at what you have down there. X times x squared plus 4. This is a linear factor, right? So I know right away I'm going to have a over that linear factor. Now, the next one, x squared plus 4, is quadratic, right? And it's not factorable. If it was x squared minus 4, yes, right? But it's x squared plus 4, so you can't factor that. So it's an irreducible quadratic, isn't it? And because it's an irreducible quadratic, what I'm going to do is I'm going to put the irreducible quadratic up here, down here. But up here, I don't put a constant. I put what? bx plus c. bx plus c is a linear expression, isn't it? We have put a linear expression on top of a quadratic. Why? Well, because the idea is that if u is the denominator, the derivative of that is going to be 1 power less, right? So if this is a quadratic, I'm trying to force the numerator to be linear. Just like here, if the denominator is linear, its derivative is a constant, right? So you could extend this idea, like if we had some cubic function down here that we couldn't factor, you could try putting a quadratic on top. But we aren't going to go there, all right? So that's it. This is what we're going to do. So we need to find a, b, and c again, don't we? Clear the fractions. 2x squared minus x plus 4 equals. Now, you're multiplying both sides by this right here. So when you multiply that by that denominator, just the x cancels. A times x squared plus 4. And then over here, plus, now be real careful here because the numerator over here is bx plus c, right? That doesn't go away, so put it in parentheses. You okay? All right. You're not okay? Do you need help? Oh, okay. Okay. You're not choking. You're not.
I'm not
Okay, all right. I mean, I don't know what I would do. I'm just, I would say, does anyone know how to help? What next? X, okay. So we have x, right? So when we multiply this side, the x squared plus 4 cancels out. We've got that. All right, look, we're getting good at this. So let's just go 2x squared minus x plus 4 equals ax squared plus 4a plus bx squared plus cx. So I just went ahead and distributed everything out. Is that all right? And then let's try and match things up. So we have 2x squared minus x plus 4 equals, let's get my x squareds here. A plus b? Yeah. And then just cx, right? There's really nothing else, just cx. And then plus 4a. So I got my x squareds out front. I got the x. There was only one x term. There was only one term without x. And then match things up. This is where your system comes from. So I'm going to match this has to be 2. This has to be -1. And this has to be 4. So we get a plus b must be 2, c must be -1, and 4a must be 4. Now this system you actually don't even need your calculator for, because we already know what a and c are, don't we? I mean, c is -1, it's right here in front of us. A is 1. So I know c is 1, a is 1. And fortunately, the first equation, if I replace a with 1, right, because a is 1, then subtract, you get b is 1. So all of these are done without any calculator, yes. 4c. Oh, yeah, I don't know why I put c is -1, a is 1, b is 1. All right, awesome. So now this new integral is going to be this, right? It's going to be this right here. All right, new integral is 1 over x, right, because a was 1, plus b was 1, so it's just x over, or x plus, sorry, x minus 1, right, because c is -1, over x squared plus 4 dx. And the first one is natural log x. This one, okay, if we do a u sub right now, what's the derivative of x squared plus 4 going to be? So you're saying do the whole denominator as u? Derivative of that is 2x. You have 2x minus 1 there. You're not off by a constant. I mean, you're off by a constant, but not a multiple, not a constant multiple. You're off by -1. It's okay. You can get around it still. Just one quick little tweak here. Split it into two integrals. Right? Do your x over x squared plus 4, and then do your minus 1 over x squared plus 4. You're allowed to do that, right? Yes. Okay, so if I do that, are we good with this being natural log x? Yes. Are we good with this being a u substitution? Basic u sub. Use the denominator. Derivative of that's 2x. You have x. You'll have to scale it. But that's going to work out. This one?
Yep.
What? You could use trig sub. That's too much work, though. What? What formula? Arctan. Formula number 17. you have 1 over x squared plus a squared. So let me write the answer down here. This is natural log absolute value of x plus, once you do the u sub here and get your thing all together, this is what you'll get. You have to scale it by a half because you get a 2x when you take derivative. So, and then this one is minus, what is that formula again? 1 over a is 2. Arctangent of x over a plus c. There it is. All right, we have one more and I have 5 minutes. But it's okay, it's going to be super fast. Y'all ready? Good. Here we go. All right, this one is actually kind of cool. You see this one right here? Easy, easy, easy now. Okay, we need 3 calculators now, right? That looks dead. The battery's supposed to come out like that? I'm kidding. Right, the motherboard's laying there. All right, so look at this one real quick. What do we have to do first? Long division, right? Now I'm going to let you could do long division on your own, okay? Do that, but check this out. This is really kind of a clever way of doing this. I think I'm doing this right. Let me see. Okay, do you agree that that numerator is the same numerator that's up here? 4x squared. What's minus 4x plus x? Sorry, plus x. Isn't minus 4x plus x 3x minus 3x? Isn't 3 minus 1 still 2? Yeah, but do you see that by doing that, I can split this integral right here and do all of this over this, and then this over this? These two match exactly, right? So isn't that just going to be integral 1 plus x minus 1 over 4x squared minus 4x plus 3? You would get the exact same thing if you did long division. Now, I'm not saying that this is a shortcut for long division. This problem just happened to almost look, these almost look the same, so I was able to just tweak it just a little bit. It is kind of cheating, but it's also kind of clever. All right, so now we would have to do this, right? So what do you do with this? So you have to look at, do we do partial fractions? The denominator is not going to factor. So you go back up to last class, and you will see we did that integral. That integral was the one where I had to make the numerator look like the derivative of the denominator, right? Now, what is telling us we have to do that? When we see this, what is telling us we have to do that instead of the partial fractions? Well, what's telling us that is when we go to factor this, it's not going to factor. Okay? This is prime, so to speak.
What would happen if completing the square?
If you complete the square on that, you might be able to get somewhere with it. The problem is you're going to have x minus 1 up top, so you have to deal with that. It's going to complicate things, because when you do completing of the square, one of these things is going to be like, let's say, x minus 2 in parentheses squared. And then you can't do a basic substitution there because you have x's up here also. So it would be complicated. Yeah, I wouldn't go down that road. Okay, I have a quiz for you. It's a take-home quiz. I don't mind if you work together, but let me just say something about that. A lot of students I've talked to, and they're like, you know, I feel like I'm getting this, but I come to the test and I just kind of blank out. If you take this quiz and you just like go run to the lab or go sit down with somebody who's going to help you, you're not helping yourself prepare for the test. So what I would do is I would take this quiz. Well, I would first make sure I've done all the homework for 6.2 and 6.3. Watch my videos, whatever. And then afterward, I would sit down with this and treat it like a test. Because your test, I told you, is going to be probably, what, 5 or 6 questions? This is a 4-question quiz. I'm going to count this quiz as 2 quizzes, all right? So I'm saying you're allowed to work together, but I'm only saying that because I don't want to say you're not allowed to work together and then I find out someone is and then they get dropped from the class. I'm a realistic person here. I understand people are going to go get help. But be careful with the help because you can hurt yourself that way. You understand what I'm saying? Yeah. Sit down with it, get your formula sheet out, put everything away, turn off the TV, turn your phone off, and time yourself. And if you can't do this, you're not ready for the test, right? So then you start working through it and you try and see where are my weaknesses? What do I need to identify? You know. Now this covers just 6.2 and 6.3. That's all it covers, all right? It's due the next time we meet, Monday, right? Do all your work on separate paper. It needs to be neat, stapled, and in order. So don't look at this. I don't know if you've ever taken a class where you've had to write a paper. I'm sure you're in college, you've had to write a paper. There's a difference between a rough draft and a final draft. I want your final draft, okay? I don't want your rough draft. So take some pride in the work you're going to turn in, all right? All right, have a good weekend.
Hey, thank you for looking at those problems.
Oh, no problem. I looked at it right away because it was bothering me.
Yeah.
But then I went and looked and I was like, oh yeah, it's just that number needs to go into the root and we're good.